The New Quantum Era,
a podcast
by Sebastian Hassinger
and Kevin Roney.
Welcome back to the podcast. We're very excited. We've got another really special guest for you today. Another person, another distinguished researcher I had the pleasure of meeting on my recent trip to Europe. Also a Dutchman, like Leo, like our last guest. Harry Burhman is a professor at the University of Amsterdam. He's a director at the CWI, and he's the director at QSoft as well. He's got a long and illustrious career in quantum information. He's going to take us through some of his earlier work, some of his areas of interest, and then we're going to dive into some recent work, which we find really exciting.
It's actually pretty cool. He gave us a preprint of a paper that is likely to be already up on archive by the time we air this presentation. But I got to read that presentation. That entire paper, and it's a powerful framework, I think, to sort of see with clarity, the nature of what will likely become the default quantum computing architecture for all systems going forward. And he's proving really cool results with respect to time complexity around that framework. So it's the paper's called Ultra-Fast Quantum Circuits for Quantum State Preparation. Many people that have got a CS background and some quantum background, I think it's pretty straightforward read, but really cool results. I thought it'd be important, Sebastian, to outline the core framework just so that going into this interview, the audience is well prepared to take on some of these ideas. But it's this almost like this core architecture he's talking about for time complexity analysis that we think is going to be, again, a standard part of the way QC is done. Is really it's a 4-layer system that's repeated over and over again. That 4-layer system is based upon the regime of quantum error correction, but as Burhman points out, we think, and he thinks, that that's got broad applicability across domains outside of quantum error correction. But those 4 layers are, first, that you set up a quantum state and you run some quantum computing gates that do these transformations, these unitary transformations, which are so important and give such advantage. But because there's noise or errors, you then do what's called a syndrome measurement. That's the second layer.
Right, or mid-computation
there
measurement.
It is. Thank you, Sebastian. Right, where you're looking at some number of the qubits that you just changed and updated. And then the third layer, the results of that syndrome measurement go to the third layer where there's a classical computation based upon that syndrome measurement, which gives you a way to perhaps nuance or adjust the quantum state for error correction or for other purposes of enhancement of the computation. And then the fourth layer, some sort of like quantum computing gates that are applied to do adjustments and correction of the errors, or furthermore enhance the computation. So that 4-layer sandwich, that 4-layer cake, so to speak, is then done over and over again. That's the framework in which this new paper and a lot of Burhman's recent research focuses on.
Yeah, I agree. Yeah, it really does feel like a foundational sort of conceptual architecture for thinking of these quantum systems, which ultimately are going to need classical computation to be harnessed, as you said, to implement error correction. And what's exciting about what Harry's talking about is that there may be near-term computational gains that can be realized by implementing that type of hybrid architecture, classical quantum architecture in the near term, which would be quite exciting.
We had such a great time with this interview. I hope you enjoy it.
All right. We are joined today with a very special guest. We're very happy to have him with us, Professor Harry Burhman. He's a Dutch computer scientist who's made significant contributions to the fields of quantum computing and complexity theory. He holds a variety of positions. He's group leader at Centrum Wiskunde and Informatica, CWI, in Netherlands. which is the National Research Institute for Mathematics and Computer Science. Additionally, a professor at the University of Amsterdam and a director at QSoft, which is a world-leading quantum information research center in the Netherlands. So we're extremely happy to have Harry with us. Thank you so much. It'd be great, Harry, if you wouldn't mind starting with sort of an explanation of how you ended up in quantum information. Everyone takes their own path, and we always really enjoy hearing the twisted tale of how people get to where they're working in now.
Thank you very much for the kind introduction and for having me on this podcast. That's really very nice, and I'm very happy that I am allowed to say something here.
Good morning. Great to have you on. Really, yeah.
Yeah. So my path into quantum information started quite some time ago. I have to say, because I started out as a computer scientist, I was really fascinated by computers when I was very young, about 12 or even younger. I mean, and computers, you have to know, were not very widely spread by then. I mean, maybe in big industry, but not in small homes like mine. And I was really fascinated by the fact that you had a computer and you could give it, you could give it a program, and you could give it tasks, and then it would just perform these tasks exactly as you told it. And if you wanted to perform a task that would never stop, it would just go on forever. And then you could stop it, of course. And I was really fascinated by the power of what such a computer could do. And initially, I thought that any problem that you had, you could write a program if you were smart enough, and then that computer would solve that program for you. Maybe it would take a while, but if you programmed smartly, it would actually solve that problem for you. And then I learned that there are actually problems that you cannot solve on a computer, which was due to a big hero of mine, Alan Turing, who proved this in the 30s. And when I first saw that result, I just didn't believe it. I thought that cannot be right. I mean, they probably didn't think hard enough on how to solve that problem.
How old were you, Harry, when you encountered Turing's theorem?
I was about that age, 14, 15 years old, and I was reading about it, and I didn't understand the proof then, but I thought, I mean, I was really blown away by the fact that you couldn't compute everything that you wanted to. So then I was really set on doing computer science and study that in the Netherlands, which I did, and I really enjoyed it tremendously. But I also found myself not so much interested in programming a computer, but more in understanding more about what this power is and what it's not also. And so I ventured into theoretical computer science and also mathematics. And then I was lucky that I could do a PhD on these topics, and to be precise, on the area of complexity theory, computational complexity theory, which deals basically with this question: which problems are computable in an efficient and fast way, and which ones are not, with the famous P versus NP problem sort of driving the field. This is a great unsolved problem, which asks for whether certain problems have fast algorithms, or proof that they don't have that. And nobody really knows how to solve that. And of course, this was a tremendous drive for me also to go into the field and, of course, solve this problem, which is way too hard, and I didn't solve it. But that's when I was doing a PhD on that. And in the early 90s, I was also in Boston as a PhD student for about a year or a little bit longer even. And at one of the conferences there was a talk of Gilles Brassard. This was maybe 91 or 92. And he talked about this new complexity class called fast quantum polynomial time, called BQP. And he showed some Oracle results, how it somehow was different from classical complexity classes, so the ones I was used to, like P and NP. And then I was really fascinated by this new kid on the block. But I thought it would be too difficult for me to venture into this because I had not studied physics.
Gilles is a pretty good salesman for quantum information science too. he makes it sound really cool.
Oh, it was extremely cool, but I wasn't sure I would be able to do it because I did not have a study in physics. I just did math and computer science.
Yeah, quantum mechanics is a steep
Yeah.
climb from computer science, no doubt.
It actually turns out it's not at all that steep, but I just thought it was extremely difficult and esoteric and hard to get into. But then a few years later, I actually had a postdoc position here in Amsterdam at CWI, and one of Gilles' students, André Bertillon, was also a postdoc here, and he gave a series of lectures on what actually this quantum computing is all about. And then I got sort of into it, and I really understood. And at the same time, also another important thing happened. That was when Richard Cleve, another person, well-known scientist from the area, also came to CWI and had a sabbatical here. And then I got really into this in an easy way, because they knew sort of the rules of the game, and they could tell me what the rules of the game were, and then I could sort of understand that and start working in it. So I really owe a lot to them. And that's how I got into quantum information and working on quantum computing.
That's really cool. And I saw you've done a fair amount of work in communication complexity as well. Is that right?
That's exactly how it started, because Richard Cleve kicked off. Well, that's not entirely true. NDIO had already also some papers on quantum communication complexity, but then Richard had the idea of enlarging the model with entanglement instead of quantum communication, sort of entanglement.
And I guess that brings the Broussard and Bennett sort of influence into communication complexity a little bit, right, with BB84.
Yeah, yes, and entanglement, and for sure, yes, absolutely, and also non-local games and Bell inequalities and all that was sort of led Richard to study this, and then he came to CWI and he had a problem where communication complexity problem actually, where he thought he had a lower bound. So he had a quantum algorithm that was very efficient. It only used, I think, 1 or 2 bits of communication and entanglement. And then actually he was struggling with the lower bound for the classical lower bound. And it turned out, and that's when I sort of started to work on this, that we could show that there was a classical lower bound of only, I think, 3 bits or something, and that there actually also was a classical upper bound of 3 bits. So we had a problem where the quantum was 1 bit, say, and classical was 3. And this was a hard sell. Somehow Richard had tried an earlier version of this paper, and it was rejected on the grounds that, and actually that paper was wrong because it had a way too big lower bound, and it was rejected on the fact that the result was sort of not interesting, but the mathematics was impeccable. And it turned out to be exactly the opposite. The mathematics was wrong, but the result was extremely interesting, and it sort of kickstarted this field.
That's fascinating. And what year would that have been, Harry?
This must have been in 97, I think.
Okay. So just after Shor's and just after sort of the interest in quantum is still on the rise at that point. So there's still, as you said, like some whatever resistance potentially at the editorial boards of papers on published journals for papers that were looking at quantum information theory. A little bit harder sell maybe than it is today.
Yes and no, because I mean, I think the after Shor's algorithm, I mean, it got really into the spotlights, and everyone was really sort of very much intrigued by what more it could do, and people still are. So it was gaining a lot of traction, but somehow the referees at this particular journal didn't really appreciate this result. But then it sort of took off, and it was for me a very easy way of getting into the field.
That's great. And you've had a very broad set of interests. I mean, I have to ask, without getting us derailed off of the quantum information theory train, but you've got some biology papers, like the first peptides, the evolutionary transition between prebiotic and how did you get entangled, so to speak, in biological papers?
Actually, when I started my studies in computer science, it was a very popular study in the Netherlands, and it wasn't entirely certain that I was allowed to study it, because if too many people apply for a study, then not everyone can take it, and they somehow have they just do a lottery then, and they flip a coin, and you're in and you're out. And so, in addition to your first choice for computer science, you had to give a second choice of what you wanted to study in case you would not be able to. You were not admitted to your first choice, and my second choice was biology, because I always was fascinated by it as well, and I still am, and I think it's also a beautiful area to work in. And at the time of these papers, or when this paper started, we were starting a biology or computational biology group here at CWI, and I was asked to be one of the members of the committee to somehow figure out how to arrange this, and who to invite, and what kind of direction it should take. And I asked a very good friend of mine to help me, a biologist, to help me with this, and he did, Peter van der Gulik, who is now actually in the group here as well as the biologist. And he actually also came to me with some computational problems in biology, and I was just so intrigued by it that we started to work on it, and these papers came out of that.
That's great. And I mean, it does feel like one of the areas that may be very strongly impacted by mature quantum hardware and quantum algorithms will be biology and biochemistry and the like.
It could very well be, because indeed these biological processes, if you look at them carefully enough, they are quantum mechanical, and sometimes you need a quantum mechanical description to understand them. And indeed, quantum computers could be of great help in simulating them and understanding them better than we currently do.
That's awesome. And then I guess QSoft was founded in 2015 or 2016, and that's sort of also I kind of think of it around the same time as sort of the Dutch all of the Dutch efforts sort of coming together eventually under quantum delta in a very powerful sort of aggregated way. And I guess that's really, in a lot of ways, that's made your focus much more narrowly on quantum computation and quantum algorithms as we sort of understand them today. So is that sort of your main focus now in terms of the areas of study?
Oh yeah, absolutely. Indeed, the QSoft started in 2015, but at that time there was no quantum delta yet in the Netherlands, though there was already this center in Delft called QTech. And my sort of worry at the time, and maybe still a little bit, was that all around, not only in the Netherlands, but all around in the world and in Europe as well, people were focusing almost exclusively on hardware and on building very stable qubits and very stable operations on these qubits. And they were not thinking too much about what kind of algorithms do we run on this hardware if we have it. So the focus was too much on hardware and hardly on software, so to speak. And so I really thought it was important to have an institute focusing mostly on the software and instead of the hardware. And that's why I started QSoft. And then, so this was 2015, and now this is much more accepted premise that indeed we have to figure out what kind of algorithms we need to run and what kind of algorithms we need to develop, and what are the problems that are really useful to run on to solve on
and
a
in
quantum.
fact, I mean, I feel like in a way your thinking has continued to evolve to now you've been talking about how important it is to think in terms of co-design. So theorists and algorithm designers influencing the design of hardware systems with an eye towards like, how do we implement this stuff? How do we actually make this stuff work in the real world eventually? Which I think is a terrific area to focus on.
Yeah, and of course the two go somehow hand in hand. You need both, right? You need software people need hardware, and hardware people need software. So it's not that one can do without the other. And indeed, you're right. You talk about this co-design, which basically says that you're developing them both together, and somehow flaws in or problems or difficulties in one area sort of get solved by the other area, and somehow demands or questions that come up from the software side give rise to maybe new hardware implementations. And hopefully we will talk a little bit about that later when we talk about this shallow circuits and mid-circuit measurements.
Maybe this is a good time to dive into that, because this is a fascinating landscape of the ramified hierarchy of all of these different time complexity and circuit complexity and communications complexity, phenomena in quantum computing. I think a lot of our audience is perhaps already familiar with the classical cases, right, of time complexity hierarchy questions. What are the big unsolved problems in this area for quantum? Is this a good kickoff?
Yeah, I mean, so certainly, that's sort of certainly one direction we're looking into. This is maybe the area of quantum complexity theory, you might call it. And indeed, you have this classical, this big open problem like P versus NP, and basically the problem boils down to proving that for certain problems we don't have fast algorithms. So the problems we solve in practice on computers, they do have fast algorithms because we can solve them. But there are many more problems we would love to solve, but we just don't know how to do it because we don't have fast algorithms. So we have to resort to approximation algorithms or sort of algorithms that sometimes don't give an answer at all, or are completely wrong. And funnily enough, we really don't know a whole lot in classical computer science. And we don't know how to prove good sort of lower bounds, we call them, proving that for a certain problem, an algorithm needs to take more than, say, a linear time. And unfortunately, we don't really know how to do that. The best we can do for specific problems is, I think, to prove a lower bound of 5 times n, so 5 times the length of the input. But for example, for problems like satisfiability, which is a key problem in this study, or the traveling salesman problem, or there's hundreds and thousands of others, we believe that there is an exponential lower bound. We believe that it takes exponentially many steps to solve instances of length n, but we're not able to prove more than 5n for this problem. And so there's a huge gap between what we can do and what we believe is true, and what we can prove is true. And so this is sort of a big problem in classical complexity theory, that we don't know a whole lot. And now the situation only becomes worse when you add quantum, because that only makes it in some sense more difficult. And our classical understanding or lack of understanding is so big that it could, for example, be that all quantum computers can be simulated efficiently on a classical computer. This is a world that is possible, although I don't think it's possible, and not many people think it's possible, but it could be the case. So and on the other hand, we believe that there are problems that you can solve on a quantum computer, for example, like simulating certain quantum systems or quantum chemical systems or physical systems. But probably the best example is factoring, due to Peter Shor's algorithm, that we believe that we know you can do efficiently on a quantum computer, but we don't think you can do it on a classical computer. So yeah, so this landscape of complexity theory has become much richer, we believe, with the advent of quantum computing, but we still don't know a whole lot there.
So an even bigger array of even bigger unsolved problems now exist. Yeah.
Yes, our problems have become bigger, but also more interesting, I would say.
Doubtless. I mean, and to what extent do you think it's possible that there could be a future where some of the classical time complexity problems, the big famous ones, could be powerfully informed by quantum information science and quantum time complexity discovery?
Oh yeah, it could very well be that by thinking about these problems in a quantum way, you get an idea on how to solve the classical problem. There are actually examples of this, not only in algorithm design but also in proofs, where by using your quantum machinery and your quantum language, quantum information language, you can prove things that are purely classical, have in a way nothing to do with quantum, but you just borrowed the ideas from the quantum world.
I guess there was that big result maybe a year or two ago, MIP star equals RE.
Exactly, that's sort of the I guess by now the most famous example, but there are many others. Example where using ideas from quantum information and also classical computer science, I have to say, they were able to prove a beautiful result that says that multi-interactive proof systems, I guess we don't have to go into exactly what that means, but again, they were entanglement assisted, very much like the model that Richard Cleve came up with. And they showed that this class is equal to the class of RE, which is all the problems that Turing was dreaming of, including his halting problem that is not decidable. And that is sort of a beautiful result in quantum information / computer science. But the amazing thing I think that comes out of this is that it implies that a certain conjecture in pure mathematics called Kahn's embedding conjecture is false. And this is just amazing, right? It just says something about a deep mathematical problem that mathematicians have thought about for quite some time. And this is now solved by techniques and ideas from quantum information.
Yeah, that paper was a tour de force, just amazing stuff.
Yeah, that's amazing. And that paper builds upon a lot of other ideas that were developed before that.
As is always the case, yeah. Do you think, I mean, from that perspective, do you think, Harry, that over time, the distinction between classical information theory and quantum information theory will erode, and it'll be just one set of tools that you deploy on, potentially in terms of application, implementation, different types of hardware, but you think of them as one sort of set of intellectual tools?
That is quite likely. Yeah, I think it shows that it's a rich tool, and I think these results also show that it's probably the right way to think about these problems. And I think this will be part of our toolkit. Just as, I mean, there's examples of this, like you can look at problems in mathematics with just real numbers. And then there are beautiful examples where if you go to the complex numbers, suddenly beautiful results fall out by just using complex numbers. And by now, complex numbers are part of our general toolkit.
Right, and they're sort of the native language of qubits, so they're unavoidable when you're thinking about quantum computers.
Yes, but then quantum information gives you an even broader toolkit, which is useful in its own right. And so I definitely think that it will be part of a more general form of mathematics, or general part of mathematics.
So it's, you and your team are playing in some really rich, interesting territory right now. I'd love to hear more about some of you and your team's recent results. There's this new paper that I think is it archive, or is it just in preprint?
Yes, it should be on the archive. Probably it probably has appeared when this podcast has appeared, but it has not appeared while we're recording it. But it should appear somewhere tomorrow or so. This is something that came out of this co-design world, where we were talking and we were also observing the quantum hardware that is currently available, and this hardware, unfortunately, is still quite noisy and unstable. And we know that if it at some point is stable enough, So the noise is suppressed enough so that the native implementations are not too noisy. Then with the use of error correction and fault tolerance, we can make logical qubits, which can be alive for much longer time than the qubits, the physical qubits that we have currently. But we're not yet there. So this regime is hopefully coming, and hopefully coming soon, but it's not yet there. And so we're currently in this regime, which John Pressfield calls NISQ, where we have this noisy qubits that we can only use for a very limited amount of time, because when you use them longer, they have completely decohered and they're completely random, and so your computation doesn't carry any information anymore. And so we were thinking of what can we do in this particular setting. So you need computations that are very fast, because if they take too much time, right, the qubits are gone. So you need, in computer science lingo, constant depth circuit, and the depth is somehow the time your computation takes, and the size is somehow what you can do in parallel. And then, in addition, sort of working towards this advent of error correction and fault tolerant computation, these circuits need to be able to do mid computation measurements. So the way that error correction works is that you have an error correcting code, and then some error has occurred, and you do a partial measurement of your qubits, which tells you what error has occurred. And then you can do with some feed forward, you do some classical computation to figure out what this error was, and then you can correct that error by some feed forward information into your quantum circuit, and then you can do another step of your quantum computation, followed again by some measurement that measures the error that has occurred now, and so on and so forth. And if you do this right, then the measurements and the errors that occur along the way don't grow, but they actually shrink, and they stay at bay. But we're not yet there, so we cannot use this paradigm yet. So we thought, can you use this maybe for something else, for computation, and in particular for generation of states? And it turns out that, and we're not the first ones to see this, that indeed having this mid-computation measurements plus classical feed-forward actually is very useful, and can help you solve problems or generate states that, if you don't have this, are sort of impossible, are impossible, I would say, to make. And we call this the LAC model, local alternating quantum classical computation, LAQCC. And the paper that has appeared on arXiv when this podcast has appeared, it actually studies this class, and also shows that there are certain interesting quantum states called the Dickey states, that they can be generated this way. And so it's a very interesting circuit, or a very interesting scenario, I think, to work with. And many of the hardware firms and implementations allow for these mid computation.
Right. Mid-circuit measurements are becoming more commonly implemented in the hardware now. That's definitely true.
Yes, and so in that paper we show a couple of examples, and then we had also a paper that actually already appeared a little bit earlier, where we also show that you can do kind of an interesting computer science problem called list decoding of of Hadamard codes, which is not something I would do in practice, but I think it's sort of an interesting problem that can be done also by these shallow circuits, by these constant depth circuits.
And so the idea, basically, Harry, is that you're using that mid-circuit measurement and classical fan-out to essentially extend the amount of computation time, right? So you cut in before the noisy qubits fall over, grab the information, do something to them, and then feed them back into, like, prepare a state, and then go back to the qubits to continue the calculation?
Yeah, yes, exactly. And if you were in the regime where you can do error correction, then this would be doing error correction. Uh, but that only works if the errors that you introduce and that the qubits incur are not too bad, because otherwise you can imagine that this will only make things worse.
Noisier, yeah.
That's the threshold theorem, right?
And how, just from a naive perspective, the first thing I think of is VQE or QAOA, existing sort of hybrid approaches. How does it differ from a variational approach?
It differs from that because there you have a circuit that runs for a short time. Then you measure, and then you measure the whole thing, not mid circuit measurement, but at the end. And then the result of that is sort of fed back into a next instantiation of the circuit. Whereas we do partial measurements, so we do a little bit of quantum and we measure only, say, a fraction of the qubits, and then do some classical computation and then continue with the qubits that we have not measured. And so it's different in that sense. And that gives you really more power.
That's interesting. And is there a sort of in your mind, in implementation, would you be able to sort of parallelize it so that you're sort of doing mid-circuit measurement from some, continuing the computation on others, and then doing mid-circuit measurement from those, so that you're sort of alternating between sets of qubits on the system?
Yes, exactly. It's indeed alternating between a little bit of quantum computation, a measurement of some of the qubits, a fast classical computation, followed by a feedback of that classical computation into the quantum circuit, and the next step of quantum computation. But these quantum computations are very short, and also we do only very few of these alternations, so that the whole thing is very short.
It's such a powerful framework. I mean, it feels like that 4-layer sandwich that you describe in the paper. It feels like that's going to become, or already is, really the standard architecture at the machine level, right, for quantum computation.
It is because the computers have to be ready for the error correction regime, where they have to do exactly this.
And so really, I mean, your result, I think, has got broad generality across the rest of the history of QC. It will help guide people towards what are appropriate problem solutions for given specific use cases on these same rigs.
Yes, and I also hope that we can somehow uncover more tricks than we and others. I mean, we're not the only ones to look into this at the moment, that we have uncovered, and that this actually can be useful even in a regime where there is error correction and fault tolerance, because you can imagine that you could do both. You could use your mid-circuit measurements and so on, both for error correction and also for some other tricks. As long as it just makes things faster, it's good.
Right. I mean, that's what sort of it conjures in my mind, is sort of the idea of a QPU as an accelerator, right, in a broader heterogeneous sort of classical and quantum system architecture, as it would be deployed sometime in the future.
Yes, yeah, but this is sort of even more sort of closer to the hardware interaction between classical computation.
Probably some cool compiler optimizations.
Yes, if this is part of the toolkit of quantum computers, then compilers can make use of it and optimize their code. Yes, I didn't even think about that, but yes, that's absolutely true. That you could try to automate this and optimize.
And in terms of the current paper, did you are you sort of thinking through algorithms that you may be able to implement in at least in toy problem sort of scale to try this theory out in implementation?
Yes, we want to try this out on actual hardware. But one of the problems is that you really need this fast classical computation in between. So you really need to talk to the real hardware.
Just drop a PC down into the dilution refrigerator and see how it does.
Exactly. Yeah. So but they need to have this anyhow when they do error correction. So
that's right.
And it is there actually also in many cases. I talked to a few people doing these experiments, and it's actually there. So yeah, I think it's quite cool. Interesting.
Yeah, I'm aware of one project. It's called QubiC. It's an open source project of the Lawrence Berkeley National Lab, funded by the DOE, and it uses a a Xilinx FPGA board for controlling superconducting qubits, and they've implemented mid-circuit measurement and feed forward. And so there's at least a research platform that sounds like it would be ready to go in terms of trying this out, which is exciting.
That's true. Yeah, that's absolutely true. And I think also the IBM computers, IBM quantum computers have this as well as others, I think. So
yeah, and their roadmap definitely combines classical and quantum in a really sort of intimate embrace. I think their plan is that for that 100,000 qubit system is that they're calling it sort of a classical or a hybrid supercomputer, I think is how they call it.
yeah, I heard indeed that's the roadmap, right? For the
That's right.
For the next 10 years or so.
That's right. Yeah.
Yeah, quite amazing.
It is. It's amazing to see, back to your reference to Turing. I mean, it feels very much like the sort of mid 40s where you've got the convergence of early stage theoretical, jumps forward, and then these very early stage hardware implementations that start to prove out some of the ideas and then challenge. And as you said, that co-design sort of life cycle kicks in, and you get accelerating sort of forward motion as a whole field, which is, I mean, it's amazing to feel like that's happening in real time around us. It's one of the most exciting things to me.
Yeah, it is amazing, and I'm actually also very much amazed by the fact that when I started in this field in sort of the mid late 90s, it was considered very esoteric, beautiful, but esoteric, and probably wouldn't lead to anything practical field. And actually, I also thought it was like that. I was just thinking, okay, this is just beautiful, and we're just having some fun. And then in a few years, people will discover that it can't work possibly, or we will lose interest and we'll do something else.
It all started as a life of the mind, and now it's wow, so many applications.
But it hasn't stopped, and it has just increased and increased, and now it's just mind-boggling how big it is and how much attention we get and how much funding goes into our field. It's really amazing.
There still could be more, though, Harry. Remember, there could be more funding.
There could be, there could be, and probably there should be if you want to make it really work. And also like big companies are very interested in this, not only for building computers, quantum computers, but also figuring out whether it is useful for from a software point of view.
Yeah, big companies and entire nation states. I mean, it's a high profile matter of strategic importance.
Yeah. So it's very important we do the right thing. And one of course point of worry is that it's extremely hyped. So you also read a lot of nonsense everywhere in the newspapers, and you see it on the internet. And it's very, very important that we keep telling the honest story. It's not a magic wand that solves every problem exponentially faster, which you sometimes see written. But it's also not something that has no potential, right? It's super interesting, and it has quite some potential, but it will not solve world hunger problems. Next.
Right. Well, and it's so challenging because it's, in a way, it's trying to describe. I mean, to try to describe what quantum may be helpful for requires explaining what classical computing is not good at, which is kind of invisible to the average, user of computers. And we do all this stuff with classical computing that's sort of part of the fabric of everyday life, and you have to sort of explain, like, yeah, but there's this other set of problems that we're not able to do with classical computers that may actually be tractable with quantum computers, and that's where the promise lies. And it's a challenging communication goal, I think.
Yeah, although it's most likely still the case that most of these intractable problems also remain intractable for quantum computers.
You're not supposed to say that, Harry. That's deflating the bubble.
I should say that because we have to tell the honest story here.
Yeah, we really like that sober view. I mean, there's so much potential, but also there's just a lot of crazy hype that I think gateways to irrational speculation. So thank you for helping introduce some clarity.
Yes, and it's indeed just a very special set of problems for which we expect some advantage, and it's this set of problems that we have to focus on.
So I wonder, Harry, could you give us some insight on what's the next big frontier for you and your group? I mean, this is a great result you just got out. There must be more down the same pathway. I mean, this must be such a rich domain of investigation. No.
Yeah. Well, I think actually everywhere you look, it's interesting. So it's like a kid in the candy store, right? Everywhere you go, it's fantastic, and you want to go there.
That's the advantage of having a job where you're attracted to complexity. The more complex things get, great.
Yes. No, but it's really true. It's sort of so many directions that you can go to, that you can go into, and that are interesting. So there's many ways to go. I particularly am very interested in. Well, we talked about this very shallow circuits and what you can do with them. But another project that I've been working on is trying to figure out which problems cannot have a quantum speed up or can hardly have a quantum speed up. I think that's also important because we have to know where to look for problems that do have a speed up, and in order to do that, you have to also know where not to look. And so this is also an area which is called quantum fine-grained complexity, where we're looking at the actual real complexity bounds for quantum algorithms compared to classical algorithms. Under a reasonable hypothesis, you can say quite a lot there. I think this is a very interesting a field that needs to be further developed. And always you have to look at a quantum algorithm and how fast it is. You have to compare it to the best and maybe best known classical algorithm, which is also not always the case. So this sort of interaction between what do classical computer scientists have developed as best algorithm compared to what we quantum computer scientists develop, this dialogue has to be there and is super important. And you also have to be defeated at some point by the classical guys, right? Because they're so clever, and they might do something that the quantum computer cannot do better. So this is an area where I'm very interested in, and I'm also pursuing at the moment. But then there's beautiful other areas, like I'm working on this thing called quantum. It's cryptography. It's quantum position verification, where you want to prove that you are at a certain location on Earth.
I saw those papers. It's just fascinating work, amazing stuff.
And they're really, that's really a very interesting problem that maybe you could even have some practical value. But the beautiful thing is that these questions that come out of those investigations, they tie in immediately to complexity theory again. And you can, for example, show that if you prove that a certain protocol is secure, then you actually solve some big open classical complexity problems.
So generalizing from a specific, essentially finding a specific solution, and then learning how to generalize out of that solution for a class of problems?
To sort of come up with a protocol and then proving the protocol is secure in a quantum way would imply things for classical complexity theory, or it implies things for classical cryptography. Also, they're sort of interesting ties. And the latest thing is that it somehow has connections with this this theory called ADS-CFT correspondence, which is something that the string theorists developed and are thinking about.
We've had some guests on that same topic. Incredibly deep and powerful stuff. Yeah.
And this now somehow connects also to this position verification tasks and quantum algorithms. And so it's just fantastic. Everywhere you look, there's something super interesting popping up.
So position verification based on quantum computation or quantum communication or quantum cryptography? I didn't read the paper. I apologize.
The problem is that you want to prove that you were at this, or that you are at a certain location, say on Earth, and you do this by interacting with some verified verifiers, trusted verifiers, and you can show that if this communication is just classical, then you cannot be You cannot have secure protocols. But if this communication is quantum, then there are some possibilities of having secure protocols under reasonable assumptions. So
That's
the
fascinating.
important thing is here that you can communicate quantumly. And the beautiful thing is that indeed there are now experiments, right? There are even quantum networks that can run these protocols.
In fact, some in the Netherlands, I think, are particularly advanced.
There's some in the Netherlands, yes, absolutely. Which is also amazing that protocols that were developed in the 90s and early 2000s now can be actually run on actual hardware.
Yeah, Ken Brown from Duke University said to us, or to me once, every year people say we can't possibly make this stuff work, and our results improve by another order of magnitude. It's like, if it can't work, I'd love to know just right now so we can stop. But it keeps improving, so we keep working at it.
Yeah. That is really beautiful to see that.
Terrific. So before we let you go, this has been super interesting. I just wanted to comment on one thing that I found really interesting. You've got an extremely long research history. There's tons and tons of papers you've been part of, and we've talked about a bunch of areas you've been involved in. But I wanted to just point out, you also seem to have a knack for coming up with really funny and interesting titles for papers. And I just want to list off my 3 favorite and get your view on them. So, I'm sorry, Dave, I'm afraid I can't do that. That's a great one.
Yeah.
Most recently, a qubit, a coin, and an advice string walk into a relational problem with Scott Aronson. I mean, admittedly, these are physicists and mathematicians jokes, but still good jokes.
I think that one was mostly due to Scott.
Scott. It does sound like Scott, yeah. And my favorite, though, is the Pirandello reference, 6 hypotheses in search of a theorem. Terrific. Really good.
Yeah, so that last one actually got us honorable mention in the Journal of Irreproducible Results.
Oh, nice.
Yes.
High honor.
Maybe you could score an ignoble prize or something off of this one, right?
But it's that journal that comes indeed with the Ig Nobel prizes, and but it's a real paper. I mean, it's science and it's solid. Yes, it's about 6 hypotheses indeed. One of them is P is equal to NP, which, I mean, all the hypotheses we believe are false, but we wanted to combine them. And actually, the theorem we wanted is that they're all equivalent, but we were not able to prove that. So that's the 6 hypotheses that are in search of a theorem, indeed. But indeed,
that's terrific.
Inspired by the Pirandello play.
Yeah, it's a favorite of mine, so I quite enjoyed that. So that's terrific, Harry. It's been super, super interesting talking with you. We really appreciate your time. All very interesting work and fascinating topics. So thank you so much.
Thank you so much.
Thanks for having me, and keep up the good job of having a nice podcast. And
you're so kind. Thank you.
Around. Yeah.
Thank you.
It's all really nice. Thanks.
Thank you. Take care.
Thanks now.
Bye-bye.
Wow, Sebastian, that was so fun. Really cool guest. Yeah. I wonder how did we come across Professor Burhman?
I've crossed paths with him a couple times professionally, and then I met him at an event in Delft when I was in the Netherlands in May. And actually, no, that's not true. I saw him in Paris first. He presented previewed some of the results that he was going to publish in that paper, the LAQCC system. And I got very excited and immediately started pursuing him as a podcast guest. It took us until now, just with summer holidays and everything, scheduling to make it happen.
Good stuff. Yeah, I guess that paper now up on archive is called Ultra Fast Quantum Circuits for Quantum State Preparation. We'll put a link, I guess, in the notes, right? That'd be good. But fun dialogue around that. What I really love is how he focused so powerfully on basically trying to snuff out the unrealistic claims about what QC can do. I mean, he's like embracing, like we try to do as much as possible, embracing the excitement of the potential of this, but still temper it, that excitement with sober expectations, because the hype is kind of wild right now.
Well, and in fact, he's even focusing now on fine-grained quantum complexity, which is looking sort of for the negative space, right? The things that it will not help for, which I think is super helpful for the progression of the field.
Yeah, realistic upper bounds and lower bounds on what QC can do. It was kind of notable. Also, he went way out of his way to point out that, really, many of the NP-complete problems out there that we know as valuable targets, and there's no efficient algorithm to do them, they'll still stand hard as difficult problems, in the era of QC. I mean, let's get real here. I mean, in a sense, he's saying that the time complexity hierarchy we've known in the past is going to be much more rich and complex than we've studied. But it's not going to just collapse.
Right.
Yeah.
No magic bullet.
Yeah, right.
Although it is also really, I thought it was really fascinating thinking about or talking about how the tools from quantum information theory are sort of merging with complexity theory, with classical information theory, and just making for a richer tool set for thinking about information science as a whole, instead of distinction between quantum information and classical information.
So agree. I mean, you could even imagine quantum information theory sometime in the near future becoming, a core part of the canon, right, of computer science. I mean, these tools are so valuable.
That's right.
It's not just for physicists anymore.
Right. And with anybody like Harry, who's, as he said, started in sort of the mid 90s, I think we both share that kind of wonder at a career where you start off with something that's, so esoteric and so impossible. It's just sort of like, as you said, the sort of something that just lives in the mind. And then to actually be at this stage in his career, seeing real world implementations of this stuff mature and get closer and closer to real productive technologies. It's an incredible time.
It really is. I mean, the arc of the subject of going from wildly esoteric, like just deep theory, towards forms of implications for nation states, large corporations, venture capital.
That's right.
It's a fascinating story,
which feeds sometimes the overhyping of the possibility of the technology. So the cycle of life. All right. Excellent. Well, thank you so much for joining us this episode. We'll be back soon with another exciting interview in the new quantum era.
So fun. Thanks for your time. Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.